So let's get started on the third video for this section. Again, this video is just going through the last two problems on the slideshow. Give it a try yourself. See if it's making sense to you. If you're not sure, go through and watch through this video and see what I did on these problems. Again, these examples are picked because there's some things that we got to pay attention to or look at on each one of those. So let us jump into this one. So this one looks like a nice polynomial, which is, at least it'll be easy to find my derivatives here. When I look at domain and range, I know it's a polynomial, so my domain is going to be all the real numbers. I know it's fourth degree, so my end behavior is going to look like this, so I don't even have to bother with my limits at infinity. I know both ends are going to go up towards positive infinity. So I'm going to start off right off the bat with my zeros. We'll go here. So if I make 0 equals x to the fourth minus 12x to the third plus 48x squared minus 64x, I can see right off the bat that I have a common factor of x. X to the third minus 12x squared plus 48x minus 64. Now I have to figure out how to factor this one. If you're really good with your patterns, you might recognize this. Otherwise, we're going to go back to some guess and check. I look at 64. 64 is 4 cubed, so I'm going to hope that maybe that works. So I'm just going to pull out my synthetic division. 1, negative 12, 48, negative 64. If I have this a minus 4, I put a plus 4 here, and I'll bring down my 1 times 4 minus 12 times 4 plus 48 times 4 is negative 64. I got a remainder of 0, so that works. And x squared minus 8x plus 16 is x minus 4 squared. So I can come along and say I have 0 equals x times x minus 4 cubed. So x is going to be 0, or x is going to equal 4. So this is kind of nice. My x-intercepts, I got 0, 0. And 4, 0. Give me some more room to work. And that also means my y-intercept will be the same as this x-intercept at 0, 0. I don't have any asymptotes, vertical asymptotes, because it's a polynomial. I don't have a horizontal asymptote because it's a polynomial. So I can go right into my derivatives, which should be nice, right? First derivative, 4x to the third. 3 times 12 is 36x squared. 2 times 48 is 96x. Now, let's see where's this one. Where's our possible critical points? Again, I look, these are all multiples of 4. Let's see what that does. X squared cubed minus 36x. No, I'm taking out a 4. 36 divided by 4 is 9. 96 divided by 4 would be 24. And 16. Now, 16 is not a perfect cube. So again, we need to go back to synthetic division and guess and check. Possible factors are 1 and 16, 2 and 8, 4 and 4, and they can be plus or minus. So we start guessing. This is the horrible part. But this one, if I guess, I'm going to start with my 1. 1, 1, -8, -8, 16, 16, and 0, and my first guess is lucky. And this is, again, oh look, x squared minus 8x plus 64. So I got 0 should equal 4 times, I got a 1 there, so that's x minus 1. And this was x minus 4 squared. So my critical points are going to be at x equals 0. Nope. X equals 1 and x equals 4. So my first derivative, let's write this down. 4x to the third minus 36x squared plus 96x minus 64. Critical points I have 1. If I plug in 1 for x, I should get negative 27 for y. So again, I'm just plugging into this equation to find my y coordinates. At 4, well, 4 is an x-intercept, so that's 4, 0. That's kind of nice. So let's clear off some space again. Oops, and kill my 64. When I'm 64. Ba-doom, ba-doom, ba-doom. Let's do the second derivative. Three times 4 is 12. 2 times 36 is 72. Plus 96, and that's a 0. Oh, let's work with this a little bit over here. Because I'm looking for my critical points. Undo that. Not my critical points. I'm looking for my possible inflection points. So I look and say 12x squared minus 72x plus 96 equals 0. These are all multiples of 12. So let's get rid of that. X squared minus 6x plus 8 equals 0. So that's x minus 4, x minus 2. So I have 4 and 2. So my inflection points can be at 4, and 4 is 0. I know that already. And we could be 2. If I plug 2 into here, I get negative 16. Now, look at this. I have a possible inflection point and a possible critical point. Whoops, not that one. At the same point. You cannot have a point that's both an extrema and an inflection point. Because if it's an extrema, the concavity is not changing, so it can't be an inflection point. If it's an inflection point, changing concavity, it can't be an extrema. So this point here is going to give us problems. So just something to bear in mind as we're looking at that. Let's look at our intervals based on our inflection points. Our intervals are going to be negative infinity to 2, 2 to 4, and 4 to infinity. So if we look for start with our critical points. 1 is here. If I look at the second derivative at 1, second derivative at 1 equals a negative 36. So at point 1, this is concave down. So 1 No, it's not a negative 36. I can't read my own writing here. It's actually a positive 36. Doesn't help when I do this ahead of time if I can't read my own writing, right? This is going to be concave up. So 127, this is going to be a relative minimum. I look over here from 2. If I check my other critical point, my other critical point is right here. Jump, jump, jump. And that looks like spam, so we're going to ignore it. So my second critical point at 4, 0 is also a place where I know the second derivative is 0, so I can't use my second derivative test on that one. So I'm going to use the first derivative test. So the first derivative at 3 equals 8. So on this interval, it's increasing. And the first derivative at 5 is 36. So this is also increasing. So we know that this is not going to be a relative extrema. We look at the second derivative at 3. We get a negative 12. So this is concave down. We look at the second derivative at 5. We get 30. Nope, this one was 16, not 36. This one's 36. That's concave up. So this is indeed an inflection point. It switches its concavity, so it is not a relative extrema. So here we're open up, we're down, we're up. We should have enough so that we can sketch this graph now. I sit in my, I need to see the points 0, I need to see 4, I need to see 2, I need to see 1. So I can pretty much stretch this out on the x-axis. So I'll go 1, 2, 3, 4. I'll maybe not quite stretch it out that much. Okay, not go backward that far. So we'll make that 5. I need to get down to at least 27. So we'll make this a negative 10, negative 20, negative 30. Points I know. I have x-intercepts at 0 and at 4. That's also my y-intercept. I know I have my critical point. My relative minimum is at 1, negative 27. 2, 4, 6, 27 is here. I have an inflection point at 2, negative 16, 2, 4, 6, and here at 4, 0. So let's draw this in. So this is a relative minimum, so this is going to be, and this is concave up on this one. Has to go up through 0, 0, and I know it's going up forever by my end behavior. At this point from 2 to 4, I switch to concave down. So I'm going to kind of switch over like this. And then here I'm going to switch to go back to concave up. And there's my graph. Woohoo! One more to go. So try this one. Get a good trig problem in. We haven't done any of those yet. Give this a try if you haven't tried it already, and then we'll talk about this. Whoops. I'm not ready for that yet. I need to do this first. When we look at our domain and range, or our domain especially, here we have 1 plus sine in the denominator. So 1 plus sine x equals 0 when sine x equals 3 pi over 2 plus 2 pi n. We got an infinite number of asymptotes on here. So we're not gonna break this up into that many intervals. We know that sine of x, we're both here, and both cosine and sine, both of x, both have a period of 2 pi. So I'm just going to look at a interval of 2 pi. And if I can describe it on that period, I know it's going to repeat because it's periodic. And I'm going to define my 2 pi period by my asymptotes. So I am going to look at this on the interval of a negative pi over 2 to 3 pi over 2. So this is going to give me one cycle of this function. And then ideally, it should just repeat because it's periodic. On this interval, it is continuous, so I don't have to worry about any asymptotes, anything funky going on there. So I'm going to use this, instead of defining this as, oh, here are my asymptotes. Well, I do know I'm bounded by asymptotes. I could make this maybe a closed interval, and then I'm going to say vertical asymptotes at negative pi over 2 and 3 pi over 2. Then I'm going to restrict myself to that domain to make this maybe a little easier to do. If I want to look at my end behavior, I don't need to, because the ends of my, I'm going to say, no horizontal asymptotes, because I know at the endpoints of this interval, I'm going up to infinity, because the denominator is going to 0. By definition, I have no limit, right? So that kind of makes that a little bit easier. So now let's look at my x-intercepts. My x-intercept is going to occur when the cosine of x equals 0. Cosine of x equals 0 is going to be at pi over 2. And 3 pi over 2. Well, this is not in the domain, so I don't have to worry about this one. So I only have to worry about this intercept at x equals pi over 2. So my x-intercept, x is pi over 2. When that's pi over 2, oh, no, that's 0 now. My y-intercept, I plug in 0 for x. Cosine of 0 is 1. Sine of 0 is 1. So this is going to be the point 0, 1 is my y-intercept. Now comes the fun part. Okay. First derivative. And let's a quotient rule again. 1 plus sine of x times the derivative of cosine is a negative sine of x minus cosine of x times the derivative of 1 plus sine x. 1 plus sine x squared. So this is going to be a negative sine x minus sine squared x minus cosine squared x. But here these are all negative. So I'm going to take out a negative 1. I got a sine x plus sine squared x plus cosine squared x. And if you remember your good old Pythagorean identities, sine squared plus cosine squared equals 1. So this is going to equal negative 1 times sine of x plus 1 over 1 plus the sine of x squared, which I can cancel one of these out. So my first derivative is actually not too bad. This is going to be a negative 1 over 1 plus sine of x. Which means no critical points, because this will never be 0. And where this is 0 to say we don't exist is the same thing as my points that aren't defined. So I do not have any relative extrema on this one. Second derivative. Well, since this is a nice constant, I'm going to rewrite the first derivative as a negative 1 times 1 plus the sine of x to the negative 1. So the second derivative going to be negative 1 times negative 1 times 1 plus the sine of x to the negative 2 power. But again, we got to chain rule this times the derivative of sine of x. So that's times the cosine of x. So negative 1 times negative 1 is a positive 1. My second derivative is going to be the cosine of x over 1 plus the sine of x squared. And where this equals 0 is going to be where does the cosine x equal 0. And that's going to again be pi over 2, 3 pi over 2. 3 pi over 2 doesn't count for the same reason it didn't count when we're talking about x-intercepts. So my second derivative is going to be cosine x over 1 plus sine x squared. And I can have an inflection point at pi over 2, 0. Oh, I don't want that one. I want this one. I like the big eraser. It's cool. Okay. So my intervals of interest are going to be negative pi over 2 to pi over 2 and pi over 2 to 3 pi over 2. So I look on this one. Again, I have no critical points, so I'm only going to worry about concavity at here. So I have a point of interest, 0, 1, so let's try that one. If I try the second derivative at 0, I'm going to get the cosine of 0 is 1 over 1 plus the sine squared. So that's going to be positive. So this is going to be concave up. For this one, I'm going to take the second derivative between pi and 3 pi over 2. Or sorry, pi over 2, 3 pi over 2. So let's just go to pi. That's going to be the cosine of pi is a -1 over, and the sine of pi is 0. So that's going to be a -1. That means that this is concave down. So concave up here, concave down there. Let's draw this puppy off of here. So we'll go pi over 2, pi over 2, pi, 3 pi over 2. And we said we should have vertical asymptotes here. Lovely asymptotes, right? We have an x-intercept at pi over 2, 0. And we have a y-intercept at, we should number this, 1, 2, -1, -2. Here, on this interval, we're concave up. And we're going to go up to our asymptote. On this interval, we're concave down. So we're going to go there. I could pick another point here, plug it into f of x to get a better idea of some point. But this gives me the rough sketch, basic idea what's going on. And again, this is periodic, so this is going to repeat every 2 pi. So that's doing one of these with trig functions. So, yeah, have at it. Keep working with this. As I said before, only 3 problems on this homework, but they're long enough problems. So work at it and bring me your questions. Enjoy.